materials, especially on the 2D, 3D hybrid perovskites. And also, I will show you result about an excitonic analysis in 3D PB-free bulk. Actually, the presence of lead is a very, very big issue, which still prevent the commercialization, the mass production of these materials. So the way to overcome, to replace lead is something that is a mandatory process in the production of these devices. So I will not spend too much time focusing on the 3D, on the description of the 3D material. Actually, just to remember, just to mention that this is a network made by lead and iodine, and in the cavities there are usually organic cations that make the system hybrid, so organic and inorganic. First applications of this material as a light harvester are from the 2009 from Professor Miyazaki, and I was very lucky to start my research about the topic when I spent 10 years in Japan working in Segawa's lab, and I got in touch several times with Miyazaki sensei, so we had the chance to exchange our mind. My one is a theoretical mind, his one is the experimental one. So after then, I started more focusing on, especially on the property of the bulk, and in particular, I focused on the role of the organic cation, and also on the role that this cation has on the so-called ambipolar nature of these materials. Actually, ambipolar means that actually electron and holes, just to make the long story short, electron and holes have the same velocity, so they behave, I mean, in a sort of a specular way. Then I focused my attention also on the possible replacement, still from a theoretical point of view, of methylammonium with other organic cations like formamidinium and guanidinium, and also I similarly focused on the replacement assayed of lead with other metallic and possibly more environmental friendly cation. So I like to cite, this is not the first time, but I want to stress this result. I mean, this paper is from 2015, and in this paper I was stressing the possibility to use guanidinium cation as a possible source for, let's say, removing the hysteresis of the JB curve, which is a feature that affects these cells. So the idea of replacing methylammonium with guanidinium, which is by definition a zero dipole organic cation, in my prediction should have to remove this hysteresis. And actually, this was just a theoretical prediction. I said February 2015. And recently I found this paper by Juan Bisquert, this is 1 month ago, where they exactly support. Usually it's a calculation that supports experimental data. In this case, I can say that experimental data have supported my theoretical prediction. So I like to spend one word just for my theoretical analysis, which. So after that, I focused my attention also on the lifetime of the hole in these materials, and also we studied the thermal transport still in methylammonium lead iodide. Later, I also put my attention on the 0D system, so on clusters, mainly focusing on the possible applicability of clusters in photovoltaic and in LED applications, and also finding possible similarities and differences between the bulk and the 3D, between the bulk and these 0D systems. Today's talk will be focused mainly on these two concepts, these two results. So I will show you, I will give you a description of the exciton behavior in these mixed 2D, 3D hybrid perovskites, and similarly on some 3D lead-free fully inorganic perovskites. I just want to, I tell you in advance that all the results here are 100% ab initio. That means that we don't use any parameter in order to get our results. As a common starting point, I have to mention the theoretical setup of our calculation. Let's say that from a theoretical point of view, the DFT theory, which is a long-standing theory that allows us to study perfectly the structural properties of materials, fails in reproducing excited states properties. In other words, DFT band gap is always affected by some methodological shortcomings, which I will skip for the sake of for the short time I have. But we have alternative. We can somehow fix this issue to calculating the gap by means of the so-called GW approach, which is based on a green function and on a screened Coulomb potential. And in this way, we can calculate the electronic gap of the materials, which is highly comparable with photoluminescence experiments. So from the gap obtained by photoluminescence experiments. But at the same time, in order to have a more quantitative comparison with experimental data, and in order to include also local field effect and excitonic effect, the step we have to follow is based on the solution of the so-called Bethe-Salpeter equation, which actually is a two-body Hamiltonian. So it's very, very, very massive in terms of computational time. The results coming from this approach are extremely takes a lot of time. But at the same time, the quality of the results, as I will show you, hopefully, show that it is worth waiting for time in order to get very nice result. So, first topic, 3D to 2D systems. This material, as perfectly introduced before by Professor Nazarudin, actually have been employed at the beginning of the 90s, were studied by David Mitzi in the IBM lab, and at that time they were used for optoelectronic application, and these systems have this stoichiometry. So A is a long chain organic cation. This one is the methylammonium, M is the metal, and N here represents the number of layers of lead, in this case lead iodine, the number of lead iodine layers in the system. Actually, for N, which is equal 1, in the case of N equal 1, we have a perfectly 2D system. Okay, while in the case of N, which is infinite, we recover the bulk system, so the 3D bulk system. So the two most employed, the two most investigated organic cations, long chain cations, are the butylammonium and the phenylethylammonium. The latter is the aromatic most investigated, and the former is the aliphatic most investigated structure, cation. Actually, the interest towards this material, just to make some story of the material, the interest towards this hybrid materials for photovoltaic in modern era, let's say in the modern era, are due to the study of Karunadasa. In 2014 in Stanford, if I properly remember, they did this material with n number of layers, which was 3. So 3 layers of this 2D, 3D system, and they found a surprising stability of this material against moisture and against air. So, in other words, the long chain cation is extremely hydrophobic. This makes the system a lot more stable than the simple, the 3D one, which is characterized by the presence of methylammonium, which at variance is extremely hydrophilic, which makes the device made with pure methylammonium extremely, let's say, easily degradable by moisture and oxidation. So, Later on, other studies have shown the interesting tunable optoelectronic properties of such material, and similarly, they show the higher stability assayed in ambient condition. So in this sense, we have a reduced concentration of lead. So later, also other papers appeared. These are the two papers of Kanazidis and my good friend Jackie Even. They did this analysis based on some parameters. They calculated they demonstrated how edge states with n larger than 2 contribute very efficiently to the dissociation of the electron-hole couple. So, and last but not least, the one I want to mention is the paper of Pedong Yang. They demonstrated the possibility of a direct growth by solution of atomically thick to they call rudest than Popper perovskite. And in this case, we can get so extremely flexible materials, and once more showing the extreme tunability of the optical properties as a function of the halide employed. So here the goal of our study is to demonstrate how considering that we are now reducing the dimensionality, and also given by the presence of a reduced screening in these systems, the many body effects are enhanced. So in this analysis, we want to provide an unbiased theoretical analysis of the presence of these bound excitons by means, as I told you, of a full ab initio DFT simulation. I will show you later that we calculate a reduced mass for such systems. And also, we will take a look to the difference between isolated nanosheets and the packed quantum wells. So these are the structures. These structures are taken from experimental data. So this is the case of N1 in the nanosheet and in the quantum well structure. And this is N equal 2, which is this is still in the nanosheet case and also in the quantum well structure. Taken from experimental data, we optimized ab initio, and on top of this material, we calculated band structures by means of the GW approach. We found that the correction I mentioned before, due to the shortcomings of DFT, so the GW calculated band gap of the material where for the sheet and quantum well are respectively more or less 2 eV in one case and 1.5 eV in the other case. So the dashed line is the DFT calculated band structure. The red line is the GW corrected band structure. We similarly calculated the optical spectra of this material, and actually we don't have experimental data to compare with our n equal 1 sheet, single sheet obtained at the Bethe-Salpeter equation level, but we have results from the paper of Blancon and Jackie Even about the quantum well. So for this system n equal 1, the quantum well, we have the black line is our calculated spectra, while the red dots are the experimental from Blancon et al. So you can see the perfect agreement between the calculated and the theoretical spectra. As I told you, this is it's a full ab initio, no parameters are used to obtain our data. We are also able to calculate the binding energy of the exciton, which actually is in good agreement with the experimental data. This is a nice picture because we, in this case, in this slide, we report the exciton spatial distribution for the case of the sheet and for the quantum well. And you can see that in the case of the sheet, let's say this point, the cross here represents the place where the hole is located, and this is the exciton, the exciton delocalization. So you can see that in the case of the sheet, of the single sheet, electron and hole are localized, of course, in the same layer, but in the case of the quantum well, once we place the hole here, the electron still remains in the same layer. So the other layers are not employed by, are not populated by exciton. And we calculated we estimated the Bohr radius, which is approximately 0.6 and 0.7, and compare to the same in the case of bulk, where we estimated a Bohr radius, let's say an exciton radius of approximately 40 nanometers. Then we pass to the structure, to the number, to the second structure, n equal 2. And in this case, we observe a correction, same approach as before. The correction here is 1.8. For the case of the quantum well is 1.3. What is remarkable here is the rise of a noticeable Rabat splitting, especially for the nanosheet here. So you can see this splitting of both the conduction band and valence band, which is due to this well-known effect, which is associated to the presence of relativistic effect, and also to the presence of a lack of centrosymmetry in these systems. So we similarly calculated the expectation value of the spin along the three directions, and we calculated as well the Rabat parameters as well, and we found a good agreement between our calculated data and that that found experimentally in this paper by these authors, by Bardeni. Even if in this case they use the phenylethylammonium, the other spacer, the other long chain, the aromatic cation I told you before. We didn't use it. This is the spectrum for the nanosheet N2, and the spectrum for the quantum well. And as before, I think that the agreement is in front of your eyes. So our calculated spectrum is in perfect agreement with the experimental, the red dot we here overlapped from the paper of Blancon and Giacomo. So our results are extremely, in this sense, we consider our results extremely successful and reliable. And we similarly show here the distribution of the exciton. As before, we put the hole here, and then this is the electron delocalization. And you can see, in this case, results for the single sheet and for the quantum well are almost the same. But here, the most important result is to observe how this exciton delocalization is more spread, at the difference with the previous case with n equal to 1. And this is in very good agreement with the experimental data, which actually reports that for a small value of n, the material is more suitable for LED application because of more enhanced photoluminescence efficiency. While in this case, increasing the number of n, the numbers of layers, this delocalization becomes larger and larger, and we can probably use these materials for photovoltaic applications. Okay. Second, last but not least, hopefully, as we shown before, we can reproduce very, very, very well some experimental data. So once we validate the setup, we can apply the same setup, hopefully for some predictive results. So in one of my previous analysis, in one of the very, very early study I did, I was interested in replacing lead with other non-toxic element in the case of the 3D systems. At that time, this paper is from 2015, 2016, so I consider it a bit old. And at that time, we have some results, experimental results from Shuzi Ayase in Kitakyushu, and where he tried to replace lead with tin with good performances, but as you well know, as we said before, tin easily oxidizes from +2 to +4. So the material is really unstable in this sense. So the idea, my idea, this is a sort of a school exercise because I was trying to replace a couple of LEDs with the two metals, which are on the left and on the right, but it's not a very brilliant idea to replace LED with thallium, which is actually even more toxic than lead. The goal of this analysis was just to try to figure out the possibility, the possible existence of materials with the same structure, but with different metallic cation in the B site. So in this sense, we characterize the material from a theoretical point of view, still from the DFT analysis. And also we found the most stable structure of this thallium bismuth combined perovskite. And here we reported details of the structures of this material. But the most important result was this one, which is the band structure of this material. This is the case of methylammonium lead iodide. This is the structure with methylammonium bismuth thallium iodide. And you can see that the conduction band is populated only by bismuth 6p orbitals, which means that there is no antibonding interaction with iodine and there is no contribution from thallium, which means that the system is not very dispersive. There is no, let's say, the effective mass, especially for what regard the electron, is not very efficient, so it's not very high. So here the idea, and this is right now we arrive to these days. The idea here is it's a sort of test analysis, and I found a paper, 1995, from a Japanese group. It's a physical review B from Matsushita. Is the author of this paper. They were claiming about the stability of this cesium, gold, and iodine system, which actually has a perovskite structure. This perovskite structure has a gold atom in the middle, but this gold atom, which in principle should be the B site cation, this proportionates towards +1 and +3. This way we are safe. I mean, we can keep the oxidation state of gold to, I mean, there is no risk to further oxidation. So, and in this case, we also know that from our DFT analysis and also from our GW analysis that the band gap of this material is perfectly matched with our single junction desired band gap. This is 1.35, calculated at the best level of theory. And most importantly, conduction band and valence band are populated by the same atoms, by gold atoms, and at the same time, the conduction band is in an antibonding fashion. So we have gold and iodine, which are combined in an antibonding fashion, and in this case, we have a larger dispersion than in the case of the double perovskite with the two, so with a quaternary stoichiometry, that is with the two metals in the B site. So this is the optical features. This one is including local field effect and excitonic effect. This one without. What we notice is this very, very large anisotropy. This large anisotropy, which it's reflected in the structure of the excitonic delocalization. This is the exciton. This is the first dark exciton of the material. This is the first bright exciton of the material. And this is amazing because this is a 3D material, but the localization, the delocalization of the exciton is a 2D material. It's just on the plane. So, to the best of our knowledge, the only system which has the same behavior is anatase. So anatase, this is a paper of my friend. They did this Angel Rubio, as far as I remember. This should be, he should be among the authors. They did the same analysis on titanium dioxide, on anatheist phase, and they found the same delocalization of exciton, or better, localization, a 2D localization. So the material is 3D, but the localization is 2D, which is, very important, because this large anisotropy can be used, of course, as a source of optical nonlinearity, and since the gap is 1.35, we can use it in the visible range. So I think that this material, even if this is, I would say, almost a complete theoretical speculation based on experimental data, but I think that this material deserves investigation. I think it's too much overlooked, because it could be possibly used in solar to energy conversion. So let me conclude. These are the main points we discussed today. So I show you the optical spectra of this layered and mixed system, showing let's say, the high reproducibility given by our theoretical approach based on Bethe-Salpeter equation. We show the presence of this Rajba splitting, which is similarly detected in still in these mixed 2D, 3D systems. And we also observed the large renormalization of the electronic DFT gap due to these quasi-particle corrections, which becomes mandatory if we want to properly study materials for photoconversion. Let me thank my my co-workers. My former co-worker is Koichi Yamashita from Tokyo University, where I spent my last 10 years, the last 10 years of my life. And right now, Maurizia, who is a source of good, always very, very good ideas, and we are with her doing this Bethe-Salpeter-based analysis. And this is the result of years of theoretical speculation. It's a book we edited with Koichi last year, and it's based on a theoretical approach for theoretical analysis for the modeling of these materials, which looks the new philosophist stone. So thank you for the attention.